Hello and welcome. Today we're going to talk about the Cauchy-Riemann equations. All right, so the Cauchy-Riemann equations are critical for understanding complex variables. This is one of the most important identities in complex analysis. Let's just get a bird's eye view here. The big question we're going to address today is, and what we've been tackling for a while now, is when or under what conditions does f prime of z exist? And, if so, what is the value? And another related question is, what is the meaning? What is the meaning of f prime of z? Or, how robust is this idea of f prime? So we're not going to get too much into the meaning here, but the idea of just saying, oh, what is the general constraints that f prime that the function has to have in order to have a derivative, and its specific form. And I think we're going to get a little bit closer to this idea of the meaning of the derivative. Okay, so let's go through and just establish a few things. First of all, f of z, we can write it as u of z plus I v of z, or even more precisely, we can write it as a multivariate function, u of x comma y, the two real and imaginary parts of our complex number, plus I v x comma y. Okay, so this function here, these two functions then have really specific things. So this function here and this function here both, well, we need to figure out something about the derivative f prime at a particular value. So let's say that z naught, we want to find the value at z naught, and z naught is actually x0 plus I y0. We want to find out this, and we know that's this limit, delta z goes to 0. And now we're going to put it in, and it's actually going to be, and then we want delta z to now be delta x plus I delta y. Okay, so we put that all in there. We can actually take it. So that's going to be x plus delta x plus y plus delta y. Now minus u at x comma y. That's one part of it. Then we have a plus I. So this is, again, just a long form expression of the derivative. It's going to be v x plus delta x, y plus delta y, minus v at x comma y. Oh, and these are y naughts, right? These are particular values that we're picking. We're fixing our function to be taking the derivative at the specific value. And then we divide by delta x plus I delta y. Okay, so as you know, any derivative, if here's our z naught point, I'll write it right here, we need to be able to take a limit as delta z goes to 0 as we go in towards this z naught point. We want delta z to go to 0 as we head towards this point here. And the idea is that it should work on any path. So as we've done before, we usually like to pick two kind of candidate paths. One will be vertically to go down, and that will be delta y going to 0, while we make, so I'll put those here, our two paths. The first path will be, we're actually going to take going in this way. It's going to be making delta y equal to 0, and then taking delta x going towards 0. So that's the path coming this way. We're also going that way. And then there's the vertical path coming up this way, and that's the other path there. It's going to be, I'll call it the second path, which is making delta x equal to 0, and then taking delta y and taking that to 0. Okay, so let's see what we can do. So here's our definition of the derivative here. So now let's just literally take that and set all the delta y's to 0. And you clearly see that this ratio then becomes u x0 plus delta x, comma y, 0, right? Because the delta y will be 0 now, minus u x0, comma y, all over delta x, plus I v x0 plus delta x, comma y0, minus v x naught y naught all over delta x. And then we're taking that limit as delta x goes to 0. And provided these functions u and v have an x derivative, I mean, we can clearly see that this is exactly ux plus I u y. Okay, so this looks pretty good. Now we have, sorry, no, I made a mistake there. This is, oh boy, I made a big mistake there. Vx, right? This is the x derivative of v, and this is the x derivative of u. All right, those are the partial derivatives of our functions here, and these are essentially real valued functions. Real valued functions, but they're multivariate functions, right? So now let's try the same two paths, but we're going to try path 2 now, okay? So we're going to try path 2, and that's going to be now our derivative. And, okay, the value has to be the same for each path, so we're going to try this second path now. And it's going to be limit as now delta y goes to 0. And now we're going to plug in delta x everywhere, and that's going to be u x naught y naught plus delta y minus u x naught y naught, and then a plus I, and that's all going to be over, what we have here is a I over I delta y, okay? Likewise, we have here a v x naught, comma, y naught plus delta y minus, I'll just call that v naught to save ourselves some typing or some writing. And then that becomes an I delta y in the bottom. All right, this looks like, again, some partial derivatives. First of all, I can multiply both sides of this by I, and that gives me a negative 1. And I can take this, which looks like a partial derivative, u y now. Likewise, I see here the I and the I cancel, and so we're left with a plus. Sorry, there's an I there, right? This I and this I multiply together, and you get a negative 1. But the I in the numerator stays there, and you get that I u y. And then finally here, we have what looks like, again, a partial derivative in y of just v by itself, so that becomes vy. Okay, so now let's see if we can write this out a little bit clearer. So I'm going to go to a new page. So what we're going to do then is, what we had there was, we had that path 1. We found that f prime, when we take the limit, was equal to ux plus vx. Okay, and then path 2, again, this was with taking delta x going to 0 and saying delta y now is equal to 0, right? And then path 2, we found a different identity. We found this one. We found negative I u y plus v y. Okay, and again, remember, f prime exists when all paths lead to the same limit. So it means that these two expressions have to be equal. Right, so we look at the real and imaginary parts, and it's clear to see that then we get from this I'm going to kind of express it very cleanly here. Here's the real part of this function, and here's the real part of that function. So we have a ux is equal to vy. Likewise, if I look at the imaginary part of both of these functions, I see a vx is equal to negative uy. Okay, so it says f prime exists when all paths lead to the same limit, which gives us this really nice condition. So this is, we can call this a condition for f prime at z0's existence. And these are called the Cauchy-Riemann equations. All right, so and that leads to a nice theorem. This is a good little test now. So this represents sort of a test. So if these equations hold, then our f prime it seems like a good candidate for differentiability. But recall that I've written down already that f prime is equal to this. All right, so what do we mean by that? When I'm doing this calculation, well, first of all, I'm assuming ux, uy, vx, and vy exist. But that's okay. I think we can make that assumption. We'll say that yes, the functions have to have partial derivatives. Okay, but we're also making this implication that we're making an assumption that this does exist. Okay. So we can actually write this down as a theorem. So when we're making the assumption that this exists, then it must be true that these equations hold. We can actually state that as a theorem. I'm going to call that theorem 1 because we're going to go over another theorem in a little second, which is if f prime at z0 exists, then the Cauchy-Riemann equations are satisfied at z0. So with all of these here, we're evaluating this at z0. So it's whether these partial derivatives agree at the point z0. So we have to do this for every point. So again, what we're saying is that ux equals vy and vx is equal to negative uy. Okay, so this is a nice theorem. Okay, so it says if there's this proposition, if that proposition is true, if this statement is true, then this has to be true as well. Well, it turns out that's okay. We derived that, but the question we wanted to answer was, does this exist, right? And this doesn't actually answer that question. It starts out with that assumption, and it leads to this conclusion. But it turns out there's a really nice perspective on this. So what we have here, this theorem, theorem 1, we wrote sort of as if A, in this case A is f prime exists, then B, ux equals vy, and vx equals negative uy, right? So that's what we wrote down. That's that theorem. But it turns out there's another version to this theorem. It's called the logical contrapositive. And it works, and it's a way of inverting if-then statements. And it simply said, and whenever this is true, so also true is this statement, if not B. Oops, I'm going to write that a little clearer. If not B, then not A. So what we're saying then is if ux equals vy Vx equals negative uy does not hold at a point z naught, then f prime at z naught does not exist. Okay, so this you can see this theorem then serves as a test or a diagnostic. It serves as a test or a diagnostic for f prime's existence. Okay, so now we have a nice test. All I have to do is test the Cauchy-Riemann equations, and if these aren't equal to each other, if any one of these equalities is violated, then we just say, okay, f prime doesn't exist. All right, so that's a nice little test, and it gives us some really nice information. But now let's go double back here, and so I said this was theorem 1. What I want to do is I'm going to state without proof another theorem. Okay, so now we're going to go to theorem 2. So this theorem 2 now goes the opposite way. So first of all, what I want, I'm going to back up before I actually state theorem 2. What we want, though, the kind of idea we want to, again, go back to our big question, which is, how can I determine when f prime at z naught exists? Okay, so now we have this nice little test. So theorem 1, I'm going to cross that out. I'll state that later, is a test for f prime not existing. So it's a kind of a negative statement, right? What I want is some sort of test for to determine when f prime does exist. Okay, so and in general, a statement if A implies B, in general, does not mean B implies A. But it turns out, in this case, we have theorem 2. Theorem 2 states then that that it doesn't actually, if the Cauchy-Riemann equations hold, then f prime does exist. So we actually do, in this case, have a B implies A. And but we have one asterisk. We need all derivatives. So we have one little side condition on this. It must be that that ux, uy, vx, and vy exist. That's not very controversial. And are continuous at z naught. Okay, and the only other minor condition that needs to be satisfied is that f itself at z exists and is continuous at in some neighborhood of z naught. Okay, and those are of course very minor conditions, but the idea is that we just need that these derivatives exist and are continuous. That's the only side condition. So other than that, now we have a nice test. So I can say, so now provided the derivatives exist, if ux equals vy and vx equals negative uy, then f prime at z naught exists, and we actually had a constructive way to compute it. F prime at z naught was equal to, and remember from the previous slide, if you go back a little ways, ux plus I vx. So we have a constructive way to prove it. And again, this is always with the proviso that these are continuous. Okay. All right, so there's our nice example. There's our nice theorem. So now we have a way of determining the existence of a derivative and actually a constructive way to compute it. As long as these derivatives, we can take the x derivatives of both u and v, we have a derivative for f. Okay, so now let's do this to actually establish a few things. I'm going to go to a new page. So we're going to do an example here really quick. First of all, let's go back to an example of something we know that doesn't exist because we've already proven it. So let's look at f of z is equal to the squared modulus of z. And that's equal to z bar, which is also equal to x squared plus y squared. All right, so let's actually, so we already know f prime of z does not exist except at z equals 0, okay? We already established that in a previous video, so let's go back and check it. So let's do this, the Cauchy-Riemann equations, which are ux, in this case is 2x. We know that vy has to equal it and that's going to be equal to, so what is ux? And so if we see right here, this is now going to be u is equal to x squared plus y squared, and v is equal to 0. All right, so vy, of course, is going to be 0. And this is only equal if x is equal to 0. All right, so that's the first Cauchy-Riemann equation. The next one is negative uy is going to be equal to negative 2y. And vx, of course, is equal to 0 again, which is only true if y is equal to 0, which is precisely what we had stated. All right, so now let's try another example. And so that, of course, uses Theorem 1. Now let's use Theorem 2. So let's talk about the function f of z is equal to e to the z. All right, we can rewrite that as e to the x times e to the I y, which is actually going to be equal to e to the x cosine y. This is using Euler's formula, plus I e to the x sine y. All right, so of course this term right there, that's our u, and that's our v. All right, so ux is equal to e to the x cosine y, right? Because I take the derivative of the x. And if I take, if I take vy, this is the Cauchy-Riemann test, it's going to be equal to e to the x cosine y. Of course, those are equal. They're continuous functions, and they're equal to each other for every x and y. So that looks good. I'm going to say check on that. And then we have also uy negative is equal to, let's look at uy. That's going to be equal to e to the x sine y. And then I want to look at vx, which is going to be e to the x sine y. And of course, those two are equal. So the Cauchy-Riemann equations hold, and they are continuous. They are all continuous functions for every x and y. It implies that f prime of z exists. Great. What is it? Well, let's calculate what it is. Remember that, I'll give myself a little bit more room here. F prime of z is equal to ux plus I vx. So we can see clearly then, we can just pull it off here. So here's ux, ex cosine y plus I, and here's vx right there, e to the x sine y. Well, that looks very similar. We can rewrite this again as that's going to be e to the x times e to the I y, which is of course e to the z. So we've just established the very important derivative that the derivative of e to the z is equal to e to the z. Great, check. Well, that's a really nice one to have. That's another identity in our kind of our front pocket there that we can have of derivatives that we can memorize. So obviously this is exactly like normal single variable real valued calculus, that the derivative of the exponential function is the exponential function. Okay, great. So hopefully that establishes some really important things here. So the next thing we want to talk about briefly is, so I'm just going to give myself a little space here. So now we have an idea of, so what does the f prime mean? How restrictive? So the meaning of f prime of z? What is the meaning of f prime? So we can't really approach this question much, but we certainly know that you know, if ux, uy, and vx and vy all exist, you know, there's no guarantee that f prime exists. Okay, so we can take the derivatives of all the constituent functions any possible way we want, but just taking these derivatives isn't enough. U and V have a very specific relationship. Essentially, U and V have to be matched for f prime z to exist. And that is the Cauchy-Riemann equations, right? We need that ux is equal to vy, and that negative uy is equal to vx, right? So if I just pick a random y vector or a random u function, it has a really specific relationship to v. We can't just pick two arbitrary functions that have derivatives in order for f prime to exist. They have to have a very specific relationship. So we find that df dz is actually very restrictive. Not any, even if all of the constituent component functions have derivatives, function in the complex plane is a lot more restrictive. And so we'll just leave it at that. And we're going to talk about more of the meanings and the specific forms of u and v that have to be true in order for derivatives to exist. We'll talk about more of that later. But now we've got a little bit more insight into that idea of the meaning of the derivative in the complex plane. So thank you very much.